Number 17, fluid dynamics. Consider distribution of mass with density. Density rho is mass over volume. And this density is, let's see, T comma X. It means when volume V is fixed, the mass inside the volume varies. That means particles are coming in and going out. So mass inside this volume is a function of time. And this density, this is as well as a function of time, it is a function of position. So this is multivariable function. In addition, there is a velocity that is also a function of time and position. Let's see. The wind blows. It is flow of air, and air consists of air molecules, and this arrow describes the direction of that flow that describes the velocity. If the arrow has a long tail, the velocity should be very large. If it is short, velocity should be small. In addition, it carries small masses. So if you place a bucket in here, in time, delta t, you will find some amount of mass is being accumulated. This mass flows comes in by passing the cross-sectional area, and it is contained in some volume with the mass, and that varies depending on time. This is the current situation. The current density, J, is defined by the product of the density. Density is mass divided by volume, multiplied by the velocity of the mass flow. You have to memorize this. Later, we'll find that this current density multiplied by the cross-sectional area, this is area vector, is a scalar product. It can be integrated over some surface, then that means the current. So what we learn in here in fluid dynamics that appears in the next semester when we study electric current. So we have to study very hard. If a steady state is achieved, steady, that means it is independent of time. That means current density, in general, it is a function of time and space, and time independent. Density, in principle, it is depending on both the t and x, but it is independent. Velocity too. So steady state indicates that the time dependence disappears and it only depends on the spatial variable. Next, if there are n identical particles contained such as molecules, contained uniformly in volume V. There is a volume V, number of particles, total number of particles, capital N, divided by the volume. This one is called number density. Number density. Total number of particles contained in a volume that is defined by with the number density. Using this number density, we can measure the density, mass density, in case these are all identical particles. Suppose that it is these identical particles are molecules, then this is mass of a single molecule, for example. In that case, mass of a single molecule multiplied by the number of molecules will be the mass of the sample. The mass of the sample should be capital M divided by volume is by definition mass divided by volume, mass divided by volume, that is density. So density can be computed by dividing mass by volume, and the mass is the number of particles multiplied by each particle's mass, and then we can see number of particles of per volume is the number density. So single particle mass multiplied by the number density is identical to the mass density. So these you are not familiar with these terminologies. However, we have to be familiar with these from now on. So now we know how to compute the current density. By definition, current density is the mass density multiplied by volume. And in here, the velocity of the flow is fixed along the x-axis. There is a uniform current density along the E1. All right. We compute flux. We compute the infinitesimal flux. We have J, current density is flowing, and we have a cross-sectional area d sigma, and it's a normal vector n hat. Then we call this d sigma vector, that is d sigma multiplied by unit vector n hat, to be the infinitesimal area vector. The current density and area vector scalar product is defined by the flux d phi, by definition. We substitute y balloon 3 multiply j dot d sigma in here, j m over L cube v E1 hat this sigma dot n hat this sigma. So we simplify this vector mass. L cube is divided into as a product of L and L square, and V is here, V over L. We have sigma, this sigma over L square. This is area. This is velocity divided by length. this should be a cosine theta, where theta is the angle between the E1, that is the direction of the flow, and the normal vector. This indicates that if they are parallel, that means the J is perpendicular to the area, the flux becomes the maximum value. If you rotate the direction so that the normal vector is perpendicular to the flow, then the flux becomes a zero. It's just like that. If you want to drink water from tap, you usually put your cup like this, so that its normal vector of the opening is parallel to the flow of water. Nobody puts the water, puts a cup like that. In that case, you cannot collect any water, because this current density J is normal to perpendicular to the normal vector of the cross-sectional area. Okay, why don't we substitute in this problem? Actually, this sigma is uniform, and this sigma can be treated as this integral is just on each face, it is just L squared multiplied by some unit vector. In here, this n hat is minus E2 hat. And here, it is E3 hat, something like that. So, integral d sigma is L squared. And suppose that it takes time t, that means Vt is the length L of this side. That it takes, if you look at this, it is rho times v, this velocity of this flow. With the length of this side, you can determine a time scale. So we introduce this time scale, then this one is expressed as the mass divided by time and multiplied by this cosine theta. This is identical to this. Okay, so from here, we can say the flux d phi is proportional to the mass passing through each surface. For example, in this case is n hat, passing through this surface per some time, given time. So mass is just like velocity is length divided by time. In this, the scale of this flux is mass per time. How much amount of mass passes through, how much amount of water passes through this cross-sectional area per unit time. So this flux indicates that amount. And this flux is actually dependent on, if you replace this mass with the electric charge, then this is a dq over dt, something like that. That is charge per unit time passing through this cross-sectional area is usually called electric current. So flux is mathematically identical to the electric current if you replace the mass with the electric charge. Okay? So after that, it took a long time to describe this very simple problem, but from now on it's a very trivial. Why they are zero? Because the flow is along this E1 direction, but E1 along the E1 direction, this area is a perpendicular. This area A is perpendicular to this J, so flux should be zero. BC, where is B? BB, BC. This plane, also normal vector is E3, but the flux is along the E1 and E3 dot E1 equals to 0. So they do not contribute to the flux. Nothing. dd prime, and here you have to determine the sign of the flux. J comes in, so mass is coming in. Normal vector of D is along this direction. What is cosine theta? Okay, and here, what is cosine theta? What is n hat? That E1. This n hat is minus E1, therefore it is a minus 1. So amount of mass, the absolute value of mass passing through this surface D is positive. The flux is positive only if the direction of the flow and normal vector of the surface are parallel. That means the flux, if the flux is positive, in this case, normal vector and current J, they are parallel. This is flux positive. In this case, flux is negative. So D prime, at D prime, flux is positive. At D, because they are opposite direction, normal vector and the flow, they are opposite. So amount is the same, but sign is negative. So the uniform mass flow is passing through D and D prime. So the amount of mass trapped inside this volume is always invariant. Why? Amount of mass coming out of the surface is m per time t. Amount of mass d prime and amount of mass coming into the surface, into this volume, that is m. They are the same in magnitude but opposite direction. So if you sum everything all together, you will find the change of mass inside the volume during the period t. However, the total sum is 0. So the mass inside the box is invariant. Okay, next one is identical to the previous problem, except that we have the velocity of the flow is arbitrary. In the previous case, we had E1, and this one was proportional to E1. This current density was proportional to E1, but we changed this one along the arbitrary direction with the polar angle theta and azimuthal angle phi. Every calculation is the same, except that what we have to replace is n prime. Here I used n prime, that is a normal vector to any plane displayed in this figure, n prime. And n is the direction of the flow, current density. So every factor is the same, except that this angular factor differs from the previous case. That can be read out from this. A has the normal vector minus E2, A prime has the normal vector is E2, and so on. So these are obtained from that way. In either way, it looks complicated, but you can always see opposite side has complicated structure, but they are of the same magnitude with the opposite direction, opposite side. These two, opposite side, opposite side. So if you sum everything all together, 1, 2, 3, 4, 5, 6 spaces all together, the sum will be indicating this change in mass inside this volume, and that is the 0. So that means mass doesn't change at all. Number 4, we are familiar with this figure. We solved this kind of problem in 16. Now we have current that is along this direction. Rho v, mass flow, comes in. Due to this flow, this lower hemispherical surface accepts mass. So mass enters into this region. And then due to this flow, mass comes out of this upper hemisphere. So I expect without any computation, I would say the net mass inside the sphere is invariant. In addition, I can make use of divergence theorem. divergence theorem over some volume that is identical to the surface integral. That surface is the boundary of this volume. Haha, this is a flux. Net flux is identical to this, and we remember J is constant. If J is constant, what is the divergence of J? Divergence of J is J x components x derivative, y components y derivative, and z components z derivative sum. Because they are all constant, it will disappear. If the integrand is zero integral over this volume is trivial integral that is zero. So sum of the flux over this closed surface must be zero. In addition, what is the amount of the flux passing through this spherical surface? What I have to do is, it is explicitly evaluated, and this evaluation over a spherical surface has been done already in 16, and I don't repeat the calculation, but this is a key point. This is a key point. J dot d sigma over the upper hemisphere and lower hemisphere. Normal vector of this hemisphere and the current, they are parallel. So this flux is a positive. So mass is going out of this surface. And lower hemisphere, normal vector and current, these flow are opposite. Magnitude is the same, but sign is opposite and negative sign. In addition, even though I have carried out complicated calculation, in fact, we don't have to compute this if I know the divergence theorem, because this sphere is a sum of upper hemisphere and lower hemisphere. And this side is empty. I can add a flat surface that is a disk whose normal vector is this, and another disk whose normal vector is opposite direction. So this single closed surface is a sum of two closed surfaces. In addition, I know divergence J is a zero everywhere. Here, divergence J equals 0, 2. Here, divergence J is a 0, 2. What happens if divergence J equals 0? Its volume integral must be 0. However, divergence theorem states that over a closed surface, flux should be the same of this integral. However, divergence J equals 0. This surface integral is 0. Haha. So if I want to integrate this integral over a upper hemisphere, there is another contribution on the disk. This disk with cross-sectional area pi r squared is placed in here, its normal vector is opposite. This is these two complicated round surface and a flat surface, simple flat surface, they construct a closed surface. And this closed surface integral should be zero. So current J passing through this pi r square. So J pi r square. J is rho v pi r square. This amount of mass passes through this disk, and the same amount of mass passes through this round surface. As a result, without carrying out this complicated integral, I can make use of the divergence theorem to state that without integral, I would say rho v pi r squared is the answer by making use of this simple integral over a flat disk. Okay? Page number 5, the same problem. V is flowing along the N, the same situation. Find the false statement. Flux passing the upper hemispherical surface, mass is coming out. Mass is coming out. Identical to the flux passing the cross-sectional circle. This is what I have done. Cross-sectional, whose normal direction is E3. So this is surface integral, and this is flat surface integral along the E3. As long as J dot this sigma integral is concerned, let's say it is S1, and let's say it's S2. S1, S2. These two are the same. So more complicated situation, very strange surface. If you are asked to compute this problem, evaluate the flux passing through this surface, it is a kind of a trap. You don't have to evaluate this integral. You just make use of divergence theorem. This integral is identical to this integral. So what you have to do is the J times pi r squared, because J is uniform, and that is rho v pi r squared. That is the answer. Lower, the same. The main reason is divergence J equals 0, and we have made use of the divergence theorem. And divergence theorem is stated in here as a closed surface. That closed surface is the boundary of a volume. And divergence J equals 0, according to the condition, it is not always true. If it is the case that this integral becomes 0, therefore this surface integral, closed surface integral, must be 0, and you can find a very simple flat surface that makes the whole surface to be closed, so that this complicated integral over curved surface can be evaluated by evaluating the surface integral of the flat surface. That is a trivial. This integral is a trivial. I have already explained all details about this, so let me pass. So this closed surface looks like a cushion. Again, I have current density, that is rho times V, and this sigma, surface area, this surface patch element has the surface area, this sigma, and normal vector and hat. And I want to evaluate the flux over a closed surface. In general, if this is the case when divergence J is not equal to 0. In that case, we'll remember this flux is proportional to the mass divided by time. So the other part, flux is coming in and this coming out. If the sum of the whole the surface integral is a positive, that means flux is positive, that means the mass coming out of this volume is a positive. That means if you impose the conservation of mass, then you will find that the mass inside the volume decreases by time t. In the limit of infinitesimal limit, as the t goes to dt, then you end up with the result that time derivative of mass with the negative sign is exactly the same as the flux that is integrated over the closed surface. Okay? Note that this mass m is contained inside this volume. If the mass flux is a positive, then the mass inside this volume decreases as time goes on. If the flux is negative, then mass inside this volume increases. All right. This one shows what I have told you. So let us consider this volume integral. This is divergence theorem for volume integral of divergence of any vector field that is true for J equals rho V2 is surface integral over a closed surface, which is the boundary of V. And that is if this J is current density, it is identical to the time derivative of mass with negative sign on it. And then why don't we replace this mass? What is mass? Mass is density times the volume. Why don't you replace this one as an integral? Density integrated over space in the volume. So this is, I have time derivative of mass and time derivative of mass. What is mass? Mass is a density integrated over space. I insert this derivative inside, then this total time derivative is replaced with a partial time derivative because I have to evaluate this time derivative before carrying out the volume integral. So in here, I obtain this. Now I replace this mass-dependent mass-time derivative of mass formula in terms of volume integral. Why don't we combine these two? This is identical to this. So I move this one to the left-hand side. And because this integral is over the same region, I combine the two integrand. This is always true. It is always true. Why don't we take this volume to be very tiny? For example, we have a point X and radius epsilon, and take epsilon very small. And this volume V is VE is always included inside this tiny sphere. In that case, this one integrand is evaluated at a simple point at X. So I can factor this integrand out. And this is a very small, this volume becomes a very small, something like that, and epsilon goes to 0, but goes to 0 does not mean epsilon is 0. It doesn't touch 0. So it's just tiny, so I can divide this both sides. I end up with a very useful relation, divergence J plus partial time derivative of density, mass density, is always 0. This is the differential form of continuity equation. This is the consequence of conservation of mass. Conservation of mass, this is the integrand form of a continuity equation. This is integrand of integral form of continuity equation. That is the consequence of mass conservation. And by making use of the divergence theorem, I have replaced the mass as a volume integral, so we derive the differential form of continuity equation. It is a very, very important formula. And divergence theorem is not only important in fluid dynamics, but also important to both gravitational field and electromagnetic field. Let's consider this problem. We have inverse square law. You remember the gravitational acceleration in general is given like that. And we use G equals 9.8 meter per second squared minus E3, for example, in case R is the radius of the Earth. However, in general, it is a function of radius. And there is a constant K that is minus gravitational constant and mass of the Earth, but it can always be replaced with any mass. It can be mass of the sun, something like that. In addition, this mathematical structure is identical to the case for the electrostatic case. So it is also true if I replace this coefficient K with 1 over 4 pi epsilon 0 and electric charge, then this one becomes electrostatic field. So we remember unit radial vector over r squared. This one divergence in the previous exam, this one appeared, we studied too many times. This one, this divergence is always zero, except for the single point, x equals 0. You remember this gravitational field is coming into the mass. In case if we have positive charge, electric field is always coming out of this charge. Except for this point, except for this singular point, everywhere else divergence vanishes. So divergence G equals 0 everywhere, except for x equals 0. Remember, divergence G does not equal to 0 at the origin. You can see it diverges. It's a negatively diverges. It is something like sink in gravitational field case. It is equivalent to the negative electric charge. That in that case, electric field converges to this one, the gravity. Finally, I can make use of divergence theorem in here. This is mathematical identity. However, this is an arbitrary volume integral. We made use of the fact we have some point where the mass is. We have volume. Everywhere, divergence G is 0. So this integral is 0 except for a tiny region that includes x equals 0. So this integral is identical to the integral over this tiny region. I would say it is a V epsilon. V epsilon is the very tiny sphere that encloses the origin where the mass is placed. So this integral reduced to a simple integral over a tiny region. All right. And then divergence here. G, I copy this G here. I have to evaluate this. However, I can replace this one V epsilon first because divergence vanishes everywhere if x is not equals to 0. And then I apply divergence theorem in here. This integral can always be evaluated on a closed surface. This V epsilon is a sphere whose center is the origin where the mass is placed. I replace this one into a closed surface integral. This is closed surface. And this vector is placed in here. Scalar product with surface element. And this surface element can be evaluated very simply if I make use of spherical polar coordinates. This is the radius of a tiny sphere, so r squared, radius squared, d cosine, d phi, and d cosine theta runs from -1 to 1, and phi runs from 0 to 2 pi. And then we have a scalar product with the normal vector of the surface and the radial vector of the radial vector. So radial vector, scalar product, that is just one, so area only. Now we substitute this one is this, and here what we find, this is angular integral, and epsilon, this one is also epsilon square, because the surface, on the surface, this radius is exactly r is exactly the same as epsilon. So epsilon cancels, k is copied, this angular integral is a solid angle for pi. Then finally, I end up with 4 pi k multiplied by unity. And unity can always be expressed as the integral of Dirac delta function. Dirac delta function is 0 everywhere, but except for the singularity at the origin. However, its integral is defined to be 1. So it looks complicated, but we already have studied it is just 1. Once we rewrite this, you end up with the fact this is divergence G. Volume integral of divergence G is identical to volume integral of Dirac delta function multiplied for pi k. And k was originally expressed as -gm. Finally, we end up with this return. The mass, point-like mass m is placed at the origin. That always makes a singularity that Dirac delta function allows us to treat this kind of singularity that mathematician doesn't want to attack the problem, but it is a physics problem. So Dirac delta function comes from the analysis of this kind of mathematical singularity, but physical phenomenon. As a result, we end up with the fact that this mass times Dirac delta function is actually the mass density. So in general, gravitational fields satisfy this very simple differential equation. That is called the Gauss law, differential form of Gauss law of the gravitational field. And you will find this is the same, identical for the case of electrostatic field. Now, the remaining pieces are trivial. Continuity equation, divergence J, continuity equation here. This is the most general case. However, steady state, time independent. So steady state divergence J equals 0. Okay, steady state. So rho is independent of time, so this continuity equation reduces to divergence J equals 0. And then current of an incompressible fluid flowing in a tube in a variable cross-sectional area as shown in the figure. Okay. Let's see. J dot this sigma inside the tube, you construct a closed surface. Closed surface. This is a closed surface. You want to compute the this is divergence theorem. Steady state, divergence J equals 0. So this is 0. And surface integral should be 0. Here, there is no mass flow tube. It is blocked. The only mass flow is this side and this side. That means this surface integral is for this and this. And they must cancel. They must cancel. Because the normal vector is along this, that is opposite to the flow. The normal vector of this surface is parallel to the flow. You will find the magnitude of the velocity is anti-proportional to the cross-sectional area. Okay? You say small a is opposite to the flow. This is, although this is positive sign, this amount is negative, and this amount is positive. And this is a positive definite. If we a is absolute value of a vector, small a is absolute value of a vector. So the reason why I have capital B here, the small cross-sectional area, has a faster flow of the current. This is the consequence of continuity equation. And this part Derivation equation is completely derived in the original version of X17. Let me ask you to review the X17 instead of, I think I don't have to explain 11 and 12. So that's it for today.